Dear students, welcome. We are discussing partial differentiation. We have already done 4 classes on partial differentiation. Today, we are going to discuss about a very important theorem which is called the Euler's theorem on homogeneous function. Euler's theorem on homogeneous function. Euler's theorem on homogeneous function. For that, we should know what is homogeneous function. Homogeneous function. Suppose consider an expression a naught x to the power n. Consider an expression a naught x to the power n, a1 x to the power n minus 1 y plus a2 x to the power n minus 2 y square plus a3 x to the power n minus 3 y cube plus a n minus 1 x y to the power n minus 1 plus a n y to the power n. Consider this expression. You see, it is a function of x and y. See, every term it is of degree n. This term is also of degree n minus 1 plus 1 degree n. This term is also of degree n minus 2 plus 2 degree n. All terms are of degree n. An expression in which all terms are of the same degree, then such type of expressions are called homogeneous function. These are called homogeneous function. Homogeneous function. Such type of functions are called homogeneous functions. Suppose f of xy equal to a naught x to the power n plus a1 x to the power n minus 1 y plus a2 x to the power n minus 2 y square plus a3 x to the power n minus 3 y cube plus a n minus 1 x y to the power n minus 1 plus a n y to the power n. A n y to the power n. It is a homogeneous function of degree n. All terms, this term is of degree n, this term is of degree n, all terms are of the same degree. This is called homogeneous function. It is a homogeneous function. Notice that this function can be written as x to the power n. You may take x to the power n common. A naught plus a1, if x to the power n is, if you take x to the power n common, then this term will be maybe written as y divided by x. Y divided by x. Y divided by x. Because multiply x to the power n into y divided by x. Y will be there, and x to the power n divided by x means x to the power n minus 1. Plus a2, this can be written as y by x whole to the power n, not n, y by x whole square, y by x whole square, plus a3 y by x whole cube, like that. You may write it like this, plus a n minus 1 y by x whole to the power n minus 1, because multiply this by x to the power n. Y to the power n minus 1 is there. X to the power n divided by x to the power n minus 1 will be equal to definitely x. X to the power n divided by x to the power n minus 1 will be equal to x. Plus a n y by x whole to the power n. You may write like this. Or simply you may write x to the power n a function of y by x. It is a function of y by x, because it can be written as y by x whole to the power 0, y by x whole to the power 1. Now, what is called homogeneous function? Another definition, we can define homogeneous function also as a function fxy is said to be a homogeneous function of degree n if it can be expressed in the form this x to the power n, another function of y by x. Another function of y by x. Now, homogeneous function. Definition, another definition of homogeneous function. Homogeneous function. Another definition of homogeneous function. A function is said to be homogeneous if it can be expressed in the form. A function, suppose two variables x, y is said to be a homogeneous function of x and y of degree n if it can be expressed in the form degree n. If it can be expressed in the form if it can be expressed in the form fxy, this is equal to x to the power n, another function of y by x, or fxy y to the power n psi x by y. If you express this function as x to the power n pi of y by x, then the function is said to be a homogeneous function of x and y of degree n, or you may express like this also. Therefore, it is a homogeneous function. A function is said to be homogeneous if it can be expressed in the form x to the power n pi of y by x. It will be of degree n. If it is of degree 2, then you will get x square pi of y by x. If it is of degree 5, then you will get then you can express fxy is equal to x to the power 5, a function of y by x. X to the power 5 function of y by x. It will be of degree 5, like that. It will be of degree 5. Now, important theorem is an important theorem. If u is a homogeneous function of x and y of degree n, then if u is a homogeneous function of x and y of degree n, u is a function of two variables x and y, also it is a homogeneous function of degree n, then del u by del x, and because it is a function of x and y, partial derivatives of u with respect to x, and del u by del y are also homogeneous function of degree n minus 1. Homogeneous function of degree n minus 1. If u is a homogeneous function of x and y of degree n, then their first derivatives del u by del x will be a homogeneous function of x and y of degree n minus 1. Similarly, del u by del y is also a homogeneous function of x and y of degree n minus 1. Let me prove this. Proof of this theory. The proof of this theory. Proof. Now, you are given that U is a homogeneous function of x and y of degree n. Therefore, we must write U is equal to x to the power n f of y by x or phi of y by x like that. Since U is a homogeneous function, U is a homogeneous function of x and y of degree n. Therefore, we may write, we must write, you may write, you must write x to the power n a function of y by x. You may write like this. U is a homogeneous function of x and y of degree n. Therefore, you may write U equal to x to the power n phi of y by x. Suppose this is number 1. We have to show that U is a homogeneous function of x and y of degree n. You must write, you may write like this. We can write like this. U is equal to x to the power n phi of y. Now we have to show that del u by del x is a homogeneous function of x and y of degree n minus 1. Now differentiating 1 partially with respect to x we get. Now differentiating 1 partially with respect to x we get. Differentiating 1 partially with respect to x we get. Del u by del x equal to, you see here, it is a product function. X to the power n is a function, phi of y by x is another function of x and y. First function x to the power n, the differentiation of the second function, phi dash y by x. Now you are to differentiate y by x partially with respect to x. Then you will get y by x square. First function x to the power n, differentiation of y by x, it will be phi dash y by x. Also, if you differentiate y by x partially with respect to x, treating y as constant, then you will get y. 1 by x, differentiation of 1 by x means x to the power minus 1. Differentiation of x to the power minus 1 is minus x to the power minus 2, means minus 1 by x square, plus differentiation of the first function n x to the power n minus 1, phi of y by x. You may write like this, phi of y by x. Or this is equal to minus x to the power n minus 2 you may write x to the power n minus 1 into y by x. You may write like this, x to the power n minus is there, y. You may write, if you write y by x in place of y by x square, if you write y by x, then x will be there in the denominator. X to the power n by x will be x to the power n minus 1. Phi dash y by x plus n x to the power n minus 1 phi of y by x. Or x, you may write x to the power n minus 1 common, minus y by x phi dash y by x plus n phi of y by x. You may write like this. You see here in, the terms within the bracket. It is a function of y by x. It is another function of y by x. This is equal to x to the power n minus 1, another function of y by x, where psi x equal to psi y by x. Psi y by x equal to minus y by x pi dash y by x plus n pi y by x. You may write x to the power n minus 1. Thus, del u by del x is equal to x to the power n minus 1, a function of y by x. Means del u by del x is a homogeneous function of x and y of degree n minus 1. Therefore, del u by del x is a homogeneous function of x and y of degree n minus 1. If u is a homogeneous function of x and y of degree n, then del u by del x is also a homogeneous function of x and y of degree n minus 1. Degree n minus 1. Now, we are going to prove that del u by del y, similarly del u by del y is also a homogeneous function of x and y of degree n minus 1. Now differentiating one partially with respect to y, we get with respect to y. If you differentiate this partially with respect to y, then you will get del u by del y equal to x to the power n. It is constant. If you differentiate this partially with respect to y, then you should treat x as constant. Therefore, x to the power n is constant. This is constant, and it will be pi dash y by x. Also, differentiation of y by x. If you differentiate partially y by x with respect to y, you will get this. This is equal to x to the power n pi dash y by x. It will be definitely 1 by x. This is equal to x to the power n minus 1, a function of y by x. Pi dash y by x. Thus, del u by del y is also that can be expressed as x to the power n minus 1, a function of y by x. Pi dash y by x. Therefore, del u by del y is also a homogeneous function of x and y of degree n minus 1. Therefore, del u by del y is also a homogeneous function of x and y, of degree n minus 1. Del u by del y is also a homogeneous function of x and y of degree n minus 1. Degree n minus 1. Now, it is very easy. What is the theorem? U is a homogeneous function of x and y of degree n. Del u by del x is also a homogeneous function of degree x, homogeneous function of x and y of degree n minus 1. Del u by del y is also a homogeneous function of x and y of degree n minus 1. Now, to test a function whether it is a homogeneous or not, then try to express it like this. Suppose you are to show that fxy, a function of x and y, is a homogeneous function of degree n. Then you must express fxy equal to x to the power n, a function of y by x, x to the power n into a function of y by x. Then it is a homogeneous function of degree n minus degree n. Similarly, if fxy is a homogeneous function of degree n, then if we put tx for x and ty for y, then if we get thus we have put tx for x, you will get tx ty. will be equal to Tx Ty will be equal to T to the power n, the function of x and y. T to the power n, a function of x and y. Then the function is said to be homogeneous. Then the function will be homogeneous. Function will be homogeneous. Then the function will be homogeneous. Now, I am going to give the statement of Euler's theorem. What is Euler's theorem? If U is a homogeneous function of x and y of degree n, then x del u by del x plus y del u by del y del u by del y equal to n times of u. This is the statement of Euler's theorem. Let me write the Euler's theorem. Before that, I want to remove this one. Now, Euler's theorem. Euler's theorem on homogeneous function. Now, Euler's theorem on homogeneous function. Theorem on homogeneous function. Euler's theorem on homogeneous function. Statement. What is the statement of Euler's theorem? If U is a homogeneous function, of x and y of degree, and then x del u by del x plus y del u by del y equal to mu. If U is a homogeneous function of x and y of degree n, then del u x del u by del x plus y del u by del y equal to mu. This is the statement. You are given that U is a homogeneous function of x and y of degree n. Therefore, we must write U is equal to x to the power n, a function of y by x. Since U is a homogeneous function, of x and y of degree, and therefore we may write, U equal to x to the power n, it is of degree n, x to the power n, a function of y by x. You may write like this. We may write U equal to x to the power n, f of y by x. Now, differentiating one partially with respect to x, we get differentiating one partially with respect to x. Differentiating one partially with respect to x, we get del u by del x equal to first function is x, the differentiation of the second function with respect to x means you will get this one. Differentiation of y by x with respect to x, treating y as constant, will be equal to this, plus n x to the power n minus 1, and the second function will be like this. This can be written as, or you may write x del u by del x will be equal to, now this x, 1x will come from here, minus x to the power m minus 1 y f dash y by x. You will get this. Y is there, x to the power m minus 1, because x 1x from this denominator will go to this, plus m x to the power m f of y by x. You will get this. X to the power m, x to the power m minus 1 means x to the power m divided by x. We have written x in the left hand side. Now, suppose this is number 2. This is number 2. Now, differentiating one partially with respect to y, we get. Now, differentiating one partially with respect to y, we get del u by del y equal to, here x to the power m will be constant, f dash y by x. If you differentiate y by x with respect to y, then you will get 1 by x into 1 by x. This means y del u by del y equal to x to the power m minus 1 y f dash y by x. Suppose this is number 3. Now, if you add 2 and 3, we get. Adding 2 and 3, we get. Adding 2 and 3, we get. Now I am writing here. X del u by del x plus y del u by del y equal to, you see here, if you add 2 and 3, x to the power n minus 1 y f dash y by x minus x to the power n minus 1 y f dash y by x. This will come to the negative. You will get this one, n x to the power n x to the power m f of y by x. You will get this. Now, from 1, x to the power n f y by x can be replaced by u. This is equal to m. Means x del u by del x plus y del u by del y. This is equal to this. Y del u by del y will be equal to this. Because from 1, x to the power n f of y by x can be replaced by u. This can be replaced by u. Therefore, we have proved Euler's theorem. This is the statement of what is the statement of Euler's theorem? If u is a homogeneous function of x and y of degree m, then x del u by del x plus y del u by del y equal to mu. If it is a homogeneous function of degree 3, then you will get 3u. If it is, then you will get x del u by del x plus y del u by del x del y equal to 3u. If it is a homogeneous function of degree 1 by 2, then you will get x del u by del x plus y del u by del y equal to 1 by 2 into u. Like this. Perhaps you have understood this. Now, we shall try to solve some problems on Euler's theorem. Now, we shall try to solve some problems on Euler's theorem. Now, problem number 1. Suppose if u equal to sine inverse, suppose x square plus y square divided by x plus y. If u equal to sine inverse x square plus y square divided by x plus y, then prove that x del u by del x plus y del u by del y equal to tan u. Then prove that x del u by del x plus y del u by del y equal to tan u. Now, prove the solution of this. U equal to sin inverse x square plus y square divided by x plus y. This means sin u equal to x square plus y square divided by x plus y. Divided by x plus y. This means sin u equal to x square into 1 plus y square by x square, x 1 plus y by x, or sin u equal to x 1 plus y by x whole square divided by 1 plus y by x. This means sin u, this can be written as x into a function of y by x, x into a function of y by x. Does sin u is a homogeneous function of x and y of degree 1? X to the power 1 is there. Does sin u is a homogeneous function of x and y of degree 1? Of degree 1. Therefore, by Euler's theorem we get. Therefore, by Euler's theorem we get. Therefore, by Euler's theorem we get x del del x of, because it is a homogeneous function of x and y. Therefore, you should write x del del x of, the function is sin u, x del del u, x plus sin u, plus y del del y of sin u, h del del x of sin u, plus y del del y of sin u should be equal to 1 into that function x del u by del x plus y del u by del y. Remember the Euler's theory, x del u by del x plus y del u by del y equal to n times of u. In place of u, you should write sin u, because here sin u is a homogeneous function, not u. Sin u is a homogeneous function of degree 1. Therefore, for n we have written here 1. This means x del del x of sin u, differentiation of sin u is cos u, del u by del x plus y, it will be again cos u del u by del y equal to sin u, or x del u by del x plus y del u by del y equal to sin u by cos u. This means x del u by del x plus y del u by del y equal to, this is tan u, it will be tan u, x del u by del x plus y del u by del y equal to tan u. Therefore, sin u is a homogeneous function of x and y of degree 1. Therefore, we have proved this one. Therefore, just in other way also you may prove this one without applying Euler's theorem. Just differentiate this with respect to x partially, del u by del x, then find del u by del y, then find x del u by del x plus y del u by del y, then you will ultimately get tan u. Now, if you apply Euler's theorem, this problem becomes very easy. Applying Euler's theorem, we can solve this very easily, very easy. If you apply Euler's theorem, it is very easy. Similar problem, if you write here x, suppose this is root x and root y, then it will be half of this. Suppose question number 2. Suppose we are going to solve the question number 2. If u equal to in the previous problem, sin inverse x square plus y square divided by x plus y. In place of this, we have written x plus y divided by root x plus root y. Then we will get we have to prove that x del u by del x plus y del u by del y equal to half of tan u. Now let me solve this problem. Very easy problem. Now solution of this one. U equal to sin inverse x plus y divided by root x plus root y. This means sin u equal to x plus y by root x plus root y. You will get this one. This means sin u equal to x 1 plus y by x. It will be root x 1 plus root over y by x. This means sin u equal to x divided by root x means it will be root x 1 plus y by x, and 1 plus y by root over y by x means y by x whole to the power half, or sin u equal to x to the power half, a function of y by x. You may write like this. It is a function, the terms within the bracket. You see 1 plus y by x divided by 1 plus y by x whole to the power half. Therefore, this is a function of y by x. Sin u equal to x to the power half pi of y by x. Thus, by definition of homogeneous function, sin u is a homogeneous function of x and y of degree 1 by 2. Therefore, sin u is a homogeneous function of x and y of degree half. Sin u is a homogeneous function of x and y of degree half. Therefore, by Euler's theorem we get x function of x and y. Therefore, you will get x del x of sin u plus y del y of sin u will be equal to half into sin u. You will get this. If u is a homogeneous function of x and y of degree n, then Euler's theorem tells us x del u by del x plus y del u by del y equal to n u. For n we have written half. For u we have written sin. This means x cos u del u by del x plus y cos u del u by del y equal to half of sin u. This means x del u by del x divided by cos u del u by del y and del u by del y equal to half of sin u by cos u equal to half of tan u. Therefore, x del u by del x plus y del u by del y equal to half of tan u. Therefore, we have solved this question number 2 also. It is very easy. Now, let us try to solve the question number 3. Now, 3. what is the question number 3? Suppose u is a homogeneous function of degree n. If u is a homogeneous function, u is a homogeneous function of x and y, function of x and y of degree n. If u is a homogeneous function of x and y of degree n, then prove that x square del to u by del x square plus twice xy del to u by del x del y plus y square del to u by del y square equal to n into n minus 1 u. You will get this. N into n minus 1. N into n minus 1. Just you are simply given that u is a homogeneous function of x and y of degree n. Then you are to prove this one. Now, solution of this question. Since u is a homogeneous function of x and y of degree n, therefore by Euler's theorem, you may write x del u by del x plus y del u by del y equal to n even. Since u is a homogeneous function of x and y of degree and therefore by Euler's theory we get x del u by del x plus y del u by del y equal to mu. Just we have written the statement of Euler's theory. You are given that u is a homogeneous function of x and y of degree n. Therefore, by Euler's theory, we may write this statement: x del u by del x plus y del u by del y equal to mu. Now, you see how the second derivatives is there. Del to u by del x square, del to u by del y square, del to u by del x del y. Now differentiating one partially with respect to x we get. Now differentiating one partially with respect to x we get. Differentiating one partially with respect to x we get. X del u by del x. X del u by del x. It is a product function. First function x. Differentiation of the second function del to u by del x square plus differentiation of the first function 1 into del u by del x plus, if you differentiate partially with respect to x, y should be treated as constant. Y del to u by del x del y equal to m del u by del x. You will get this. Now multiply this by x. Multiplying by x we get. Multiplying 2 by x we get. 2 into x. 2 into x implies, this means multiply the equation number 2 by x. You will get x square del to u by del x square plus, write this term, xy del to u by del x del y equal to nh del u by del x minus, if you multiply by x, then minus x del u by del x n into n minus 1 into x del u by del x. You may write like this. N minus 1 x del u by del x. Multiply by 1 x del u by del x. N in the right hand side n x del u by del x del u by del x common, then you will get n minus 1. Suppose this is number 3. Number 3. Now differentiating one partially with respect to y, we get. Now differentiating one partially with respect to y. Differentiating one partially with respect to y, we get. Differentiating one partially with respect to y, we get h del to u by del y del x with respect to y, and x is constant here, plus first function y del to u by del y square plus 1 del u by del y. Y, differentiation of del u by del y with respect to y. Del u by del y into 1 equal to n del u by del y, or you may write x del to u by del x del y plus y del to u by del y square equal to n minus 1 del u by del y. Suppose this is number 4, and we have used this one. Del to u by del x del y equal to del to u by del y del x. We have applied this. Del to u by del x del y equal to del to u by del y del x. This means now 4 multiplied by y. 4 into y implies multiplying 4 by y, we get xy del to u by del x del y plus y square del to u by del y square equal to n minus 1 into y del u by del y. Suppose this is number 5. This is number 5. Now add 3 and 5. Adding 3 and 5 we get. Adding 3 and 5 we get. Adding 3 and 5 we get. You see, in the left hand side 4 terms are there. First write x square del to u by del x square. First write this. Then xy del to u by del y square, xy del to u by del x del y, del to u by del x del y. This will be 2 times of xy del to u by del x del y plus y square del to u by del y square, y square del to u by del y square should be equal to, we have written all the terms in the left hand side, should be equal to here n minus 1 x del u by del x, n minus 1 y del u by del y, n minus 1 common equal to n minus 1, it is common, and in the bracket you will get x del u by del x plus y del u by del y, x del u by del x plus y del u by del y. Now by 1 it can be replaced by any, this is equal to n minus 1 x del u by del x plus y del u by del y equal to n u. This is equal to n u. Thus this is equal to this. Proved. We have proved this question also. It was question number 3. If u is a homogeneous function of x and y of degree n, then x square del to u by del x square plus this terms will be n into n minus 1 u. We have proved this one. Now let us try to solve the question number 2. Question number 2. Question number 2. If u equal to x, suppose x, a function of y by x, a function of y by x, plus psi of y by x, another function of y by x. This, then prove that. Then prove that. Then prove that x square del 2u by del x square plus twice xy del 2u by del x del y plus y square del 2u by del y square equal to 0. We have to prove this. This is equal to 0. If u equal to x, phi of y by x plus psi of y by x, then we have to prove this one. Solution of this one. This is the solution of this one. U equal to x phi of y by x. It is given. Given that plus sine of y by x. It is given. Suppose it is number 1. Suppose this is number 1. Let z1 equal to x phi of y by x. This is number 2. z2 equal to suppose psi of y by x. It is number 3. This is number 3. From 1, 2 and 3 you will get u equal to z1 plus z2. From 1, 2 and 3 we will get. From 1, 2 and 3 we get u equal to z1 plus z2. U equal to, for this you write z1, for this you write z2. X u equal to z1 plus z2. Suppose this is number 2. This is number 2. Now x, therefore x, suppose x del u by del x plus y del u by del y, what will be this? Equal to x del x of, for you may write z1 plus z2, z1 plus z2 plus y del y of z1 plus z2, del y of z1 plus z2. You may write like this. This means x del u by del x plus y del u by del y equal to x del z1 by del x plus y del z1 by del y. X del z1 by del x plus y del z1 by del y. We have written this and this plus x del z2 by del x plus x del z2 by del x plus y del z2 by del y. You may write like this. X del z2, we have written this one. Suppose this is number 5. This is number 5. Now observe number 2, equation number 2. What is this? z1 equal to x phi of y by x. z1 is equal to x phi of y by x. This means that z1 is a homogeneous function of x and y of degree 1 from 2. Z1 is a homogeneous function of x and y of degree 1. Z1 is a homogeneous function function of x and y of degree 1 x and y of degree 1. Therefore, by Euler's theorem we get Z1 is a homogeneous function of x and y of degree 1. By Euler's theorem we get x del Z1 by del x plus y del Z1 by del y equal to 1 into Z1. Degree 1 means 1 into Z1. This is equal to Z1. Suppose this is number 6. This is number 6. Z1 is a homogeneous function of x and y of degree 1, x to the power 1. From 3, Z2 is a homogeneous function of degree 1. Degree 0, because you may write Z2 is equal to x to the power 0 into psi of y by x. From 3, Z2 equal to x to the power 0 psi of y by x. That is, Z2 is a homogeneous function of x and y of degree 0, x and y of degree 0. Therefore, by Euler's theorem we get. Therefore, by Euler's theorem we get x del Z2 by del x plus y del Z2 by del y equal to 0. It will be 0. Suppose this is number 7. 0 into Z2 equal to 0. Right? 0 into Z2. No problem. 0 into Z2 equal to 0. This is number 7. Now, using 6 and 7 in 5, x del Z1 by del S, this can be replaced by Z1 and this is equal to 0. Using 6 and 7 in 5 we get. 6 and 7 in 5 we get. 6 and 7 in 5 we get. 6 and 7 in 5 we get x del u by del x plus y del u by del y equal to, this can be replaced by Z1 and this can be replaced by 0. That is, this means x del u by del x plus y del u by del y equal to Z1. Suppose this is number 8. X del u by del x plus y del u by del y equal to Z1. We have got this. Now, we have to show that x square del 2 u by del x square plus this one plus this equal to 0. Therefore, you have to differentiate 8 partially with respect to x and y. Now, differentiating 8 partially with respect to x and y we get. Differentiating now differentiating. Differentiating 8 partially with respect to x we get. Differentiating 8 partially with respect to x we get x del 2 u by del x square plus del u by del x plus y del 2 u by del x del y equal to del z1 by del x. Suppose this is number 9. Multiply 9 by x. 9 into x implies multiply 9 by x we get x square del 2 u by del x square plus xy, write this term, del to u by del x del y, plus x del u by del x equal to x del z1 by del x. Suppose this is number 10. This is number 10. Now, differentiating 8 partially with respect to y we get. Now differentiating differentiating 8 partially with respect to y we get x del to u by del y del x. For del y del x, we write del x by del y plus y del to u by del y square plus 1 del u by del y equal to del u by del z1 by del y. This is equal to del z1 by del y. We will enumerate like this. This means, or enumerate x del to u by del x del y plus y del to u by del y square plus del u by del y equal to del z1 by del y. Suppose this is number 11. This is number 11. Now, multiply 11 by y we get. Multiply 11 by y we get. Multiply 11 by y we get. 11 into y. 11 into y implies xy del to u by del x del y. Here enumerate, since del to u by del x del y equal to del to u by del y del x, del to u by del y del x plus y square del to u by del y square plus y del u by del y, y del u by del y equal to y del z1 by del y. Suppose this is number 12. This is number 12. Now 10 and 12. 10 plus 12. Adding 10 and 12 we get 10 plus 12 implies, means adding this 10 and this 12 we get. Let them say right x square del to u by del x square plus, it is 10, we have written this xy del to u by del x del y. Here xy del to u by del x del y will be equal to 2 times of xy del to u by del x del y, you may write like this, plus we have written this, plus y square del to u by del y square. We have written this one also. Now x del u by del x plus y del u by del y. Write this, x del u by del x plus y del u by del y. Write this equal to x del z1 by del x plus y del z1 by x del z1 by del x plus y del z1 by del y. Now see the equation number 6. Right hand side, x del z1 by del x plus y del z1 by del y equal to z1. By 6 you may write z1. Also by 8 by 8. Enumerate, it is also Z1. It is also Z1. Now, this means x square del 2u by del x square plus twice xy del 2u by del x del y plus y square del 2u by del y square plus it is z1 by 8. This is equal to again z1 by 6. There, since by 6, enumerate since by 6 x del z1 by del x plus y del z1 by del y equal to z1, and by 6 by 8 and by 8 this one x del u by del x plus y del u by del y equal to again z1, again z1. Z1. This Z1 will be cancelled. From this you will enumerate. This means x square del 2u by del x square plus twice xy del 2u by del x del y plus y square del 2u by del y square equal to 0. Proved. We have proved this. Proved. We have proved this. X square del 2u by del x square twice xy del 2u by. Therefore, we have proved this. Dear students, we have proved. We have done 4 problems so far. Some more problems will be solved in the next class on homogeneous function. We shall apply Euler's theorem on homogeneous function. Today I want to stop here. Thanks for attending the class. Thank you very much. Thank you.